I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see understanding Bayesian networks and inference techniques. Studying Bayesian networks and inference techniques is essential for understanding how to model uncertainty, analyze dependencies between variables, and make informed decisions in complex systems. Bayesian networks provide a structured way to represent probabilistic relationships, making them useful in diverse fields such as medical diagnosis, fraud detection, and AI based decision making. Inference techniques, including exact methods like enumeration and variable elimination, along with approximate methods like Monte Carlo sampling, allow for extracting meaningful insights from these networks. Mastering these concepts enable the development of intelligent systems that can reason effectively under uncertainty, making them crucial for advanced research and real world applications. We'll see one by one. First, first, you should know what do you mean by Bayesian networks. The definition for Bayesian network is a BN. We are shortly calling it as BN. Is a probabilistic graphical model that uses a directed acyclic graph. This directed acyclic graph, we are calling it as DAC. DAC represents a directed acyclic graph. DAC, we can call it as. It is used to represent a set of random variables and their conditional dependencies. Each node in the graph represents a variable and the directed edges show how one variable influences other. The primary purpose of this DAC, that is directed acyclic graph of a Bayesian network, is to combine probability theory. It combines two theories, probability theory and graph theory, to model uncertainty effectively. By capturing dependencies between variables, Bayesian networks allow us to compute the likelihood of various outcomes, making them useful in decision making, prediction, and diagnosis. And the key components of Bayesian networks are there are three things we should know: nodes, edges, and conditional probability tables, CPTs. Nodes, otherwise we are calling it as variables. Nodes represents the random variables in the system, which can be either discrete or continuous. Discrete means what? A finite set of states. Discrete mean here you will have finite set of states, and continuous means infinite range of values will be there. That is the difference between discrete and this infinite range of values. These variables define the states or conditions that the model evaluates. Next, edges, that we are calling it as the dependencies. Edges represents the conditional dependencies between variables. A directed edge from one node to another indicates that the parent variable influences the child variable. These dependencies help in defining how information propagates through the network. Next, conditional probability table, we are calling it as CPTs, conditional probability tables. Each node in the Bayesian network is associated with a conditional probability table, CPT, that quantifies the effect of parent nodes on the child node. The CPT defines the probability distribution of a node given its parent node. If a node has no parent, it is assigned a prior probability. This is an example problem of Bayesian network. So in this example, we consider a situation where burglary or an earthquake may trigger an alarm. May trigger an alarm. If the alarm is triggered, this will be notified. Alarm is triggered, so notified to the concerned persons to take care of this process. And here B represents the burglary effects, and E is the this right arrow. This arrow represents the earthquake affects the alarm. This burglary also will affect the alarm. And here this A, here the A represent, this may be A here. A represents the alarm. And this graph, what is the function of the graph is, the graph shows that the occurrence of burglary or earthquake increases the likelihood of alarm going off, which in turn influences whether the police are noticed or not. The relationship between these variables are represented by conditional probabilities here, and allowing inference about one variable based on the state of the other. How we are going to infer? So inference in Bayesian network is explained by enumeration. Enumeration means this method computes the exact probability of query by summing overall possible configurations of the variable. It is computationally expensive for large networks. And variable elimination. In this case, this approach improves the efficiency by marginalizing irrelevant variables. It systematically removes unnecessary variables while computing exact probabilities. Next, belief propagation. This technique, also known as the message passing, propagates probabilities across the network to update beliefs about unknown variables based on known observations. And approximate inference methods. Here, Monte Carlo sampling and Gibbs sampling, we are using it. This MCMC means Monte Carlo sampling, uses the random sampling to approximate the posterior probability distribution. Mainly it is used to posterior probability distribution. Probability distribution. It is useful when exact inference is computationally infeasible. Next, Gibbs sampling, a specific type of MCMC that is iteratively samples from the conditional distribution of each variable, covering to the joint distribution over time. And how you are going to learn the Bayesian networks? Learning the Bayesian network. Structure learning. Structure learning involves identifying the graphical structure of a Bayesian network from data. The goal is to find the optimal structure that best represents the relationship between variables. Next, constrained. In this constrained based methods, these methods use statistical tests to determine independence between variables and construct network that satisfy the constraint. The PC algorithm is well-known example. Next, score-based algorithm methods. These methods assign scores to different network structure and select one with the highest score. Popular scoring techniques include Bayesian Information Criterion, BIC, Bayesian Information Criterion. AIC means Akaki Information Criterions. Next, parameter learning. Thus, once the structure is defined, parameter learning involves estimating the conditional probabilities, that is CPTs, that define the relationship between variables. Next, maximum likelihood estimation. MLE maximizes the likelihood of observed data to estimate parameters. And Bayesian estimation methods incorporate prior beliefs and update them with the data to refine parameter estimations. Next, applications of Bayesian networks. It is used in the medical diagnosis. Bayesian networks are extensively used in medical diagnosis to predict the likelihood of diseases based on observed symptoms. For example, a Bayesian network can infer the probability of heart attack given symptoms such as chest pain, shortness of breath, and high blood pressure. Next, it is used in the fraud detection. How it has been used in the fraud detection? Bayesian networks play a key role in identifying fraudulent activities by analyzing transaction patterns. They evaluate features such as transaction amount, location, and frequency to estimate the likelihood of fraud. And also it is used in the NLP. NLP means natural language processing. Bayesian networks are used in NLPs to model the world prediction, part of speech tracking and language modeling. They capture contextual dependencies to improve the accuracy of text processing and systems. Next, it is also used in the autonomous systems. In robotics and autonomous vehicle, Bayesian networks helps make decisions under uncertainty by considering various sensory inputs and environmental factors. This we have seen it in the previous lectures, and it has advantages and also some limitations. Advantages are handles the uncertainty. Bayesian networks provide a robust framework to handle incomplete or uncertain information. And explainable decision models, it is used. The graphical representation and probabilistic reasoning makes the decision making process transparent and interpretable. And it supports the qualitative and quantitative reasoning. How means the Bayesian networks allows for combination of data driven and expert knowledge based models. And the limitations of Bayesian networks are the computational complexity. As the network size increases, exact inference and learning becomes computationally expensive, and structure specification, manually specifying the correct network structure is difficult, especially in complex domains. And also, so real world cases also it is being used, like a medical decision support system, weather prediction, so many applications it is being used. So the example of the Bayesian network, as we have mentioned, burglary earthquake problem, it has been represented, the topology wise it is been represented, burglary earthquake alarm, it is connected like this. And also when the alarm will run, John, when John calls, and when the John and Mary calls, when alarms runs. The John and Mary calls conditionally independent given alarm. Both are independent. Similarly, burglar and earthquake are independent a priori, but dependent on both the cases are dependent on alarm. But as far as this John and Mary are considered, both are independent, conditionally independent. But these burglary and earthquake are independent a priori, but dependent on what? Given alarm. This is known as explaining a way. And it how it has been used semantically means, the each node is conditionally independent. Burglar, earthquake, John, and Mary, independent of its node. Sense given its parents, each node is conditionally independent of the rest of the network given at Markov blanket, its parents, its children, and its children parent. These concepts play a large role during the inference. And the global semantics, we will, in terms of probability, we will write like this. The full joint distribution is defined as the product of the local condition. Probability of x1, x2 up to, we can write it as multiplication of I is equal to 1 to n, probability of xi given parent of xi. Here, if you are taking probability of John calls, Mary calls, alarm runs without burglary and earthquake. It is not had happened, but unfortunately, this alarm runs. So we will write it as probability of John calls for the John when alarm runs. Similarly, probability of M given A, probability of A given, that is alarm given for burglary not happen, earthquake not happen, and separately we are writing probability of burglary not happen, probability of earthquake not happen. So we have to write it in terms of full joint distribution format. So how to construct the Bayesian network? We have to choose the nodes x1, x2 and I2 1 to n and add xi into the network. Select the parent node and we have to write a probability of xi given x1 up to xi minus 1. So these choices of the parent current is probability of x1 to x1 is equal to, this is the product of I is equal to 1 to n, probability of xi given x1 to xi minus 1. This rule is called the chain rule. So we have to write like this. And the example, another, suppose we choose the ordering, how we are going to choose the ordering means, first, Mary calls, John calls, alarm rings, burglary happened, earthquake happened. How we are going to draw the graph means, Mary calls, John calls, when they will call when alarm rings. And then burglary happened, earthquake also happened. So in this case, we have to draw the graph like this. So how we are going to write the probability means probability of John calls, Mary calls equal to probability of John calls. This is John, Mary or no. Otherwise, we can write like this: probability of alarm runs for both John and Mary calls. So what about probability of John calls? So many ways we will write it as no. The answer is no. The probability of B given A, J, M is equal to probability of yes. Probability of B given A, J, M, probability of B, no. And the probability of earthquake happened, no. Earthquake happened, burglary happened, alarm runs, John calls, Mary calls. Earthquake happens alone, and here alarm runs, no. So in this way, we can write in many ways. And next, by making use of the above concepts, we will introduce another new technique called inference by enumeration. So, enumeration, I have told you already. What do you mean by enumeration? Why we are going for enumeration? The definition for the enumeration is the inference by enumeration is a method used in Bayesian network to calculate the exact probability of a query variable by summing over all possible configurations of the other variables. The purpose of this enumeration is to compute the posterior probability of a query variable by marginalizing out irrelevant variables from the joint probability distribution. So here the key concepts in inference by enumerations are joint probability distribution, marginalization, and conditional probability. This joint probability already we have seen. It represents the combined probability of all variables in the network. Marginalization means summing over all the irrelevant variable to compute the probability of the query variable. Conditional probability means computing the probability of variable given evidence about other variable. So for the given burglary earthquake problem, we can draw the enumeration tree like this. This is the burglary happens. First note, the probability of burglary happened means burglary had happened means 0.001. Here, this may be earthquake may occur or may not occur. Yeah, occur means 0.002 and 1 minus 0.002 is equal to 0.998. This is not had happened. From this, we will write it as we are going to sum all those. Burglary probability of alarm happens, both burglary and earthquake happen. The probability is 0.95. A bar alarm not happen, and here B E 0.05. From this, we can extend John calls when alarm rings, Mary calls when alarm rings. Here, John calls alarm not ringing, Mary calls. Unfortunately, they may be calling means if A bar, we have to write like this. Similarly, A given B, alarm happened, burglary happened, earthquake not had happened. Now here alarm not happened, same burglary or earthquake not happened, and we are extending. If you are extending the graph like this, burglary of John calls alarm rings, and John calls alarm is not rings. Mary calls if alarm rings. Mary calls alarm not rings. So in this way, we will draw the enumeration tree by making use of the given the example problem. Any example problem given, you can be able to draw the enumeration tree. So in this case, Mary calls, John calls, earthquake had happened, earthquake not had happened. Okay. So in this problem, in this case, we'll have some more the issues will be there. What do you mean by the issues are repeated computation? Inference by enumeration often performs repeated computations because it recalculates the same intermediate results multiple times. For example, when summing over possible values of hidden variables, the same here many variables we are going to repeatedly using it. Same term may be influenced repeatedly in different branches of the summation. As a result, the computational cost increases exponentially with the number of variables. This redundancy makes enumeration inefficient, especially for large Bayesian networks where the exact inference becomes computationally interactable. Next, irrelevant variable. Another problem with enumeration is the inclusion of irrelevant variable that do not influence the query or the evidence. Specifically, any variable that is not an ancestor of the query or evidence node is conditionally independent and does not affect the final probability computation. However, enumeration still processes these variables unnecessarily, leading to wasted computational effort. By ignoring these irrelevant variables, more efficient inference can be achieved. What is the solution for this to reduce these problems? The way, first, eliminating the repeated computation. Variable elimination addresses the issue of repeated computation by storing intermediate result during the inference process. Instead of recalculating probabilities multiple times, it catches these intermediate results, allowing them to be reused when needed. This reduces the overall computational complexity and makes the process significantly faster, especially for larger networks. Next, handling irrelevant variables. Variable elimination also improves the efficiency by ignoring irrelevant variables that do not impact the query or evidence. Since irrelevant variables do not affect the final probability, they can be marginalized out, simplifying the overall computation. By focusing only on relevant variables, variable elimination ensures that computational resources are used more effectively, leading to faster and more accurate information. So the solutions are eliminating repeated computation, handling irrelevant variables, and efficiency boost. So in this way, we can eliminate the variable elimination. Coming into the conclusion that Bayesian networks provide a powerful framework for modeling uncertainty and capturing relationship between variables using probability and graph theory. Understanding inference techniques such as enumeration, variable elimination, and approximate methods is essential for deriving meaningful insights from these networks. While exact methods offer precise results, they can be computationally intensive, making approximate techniques preferable for larger networks. Mastering these techniques enables efficient decision making and predictive analysis in complex and real world scenarios. Hope everyone understood this concept about Bayesian network and its inference. The remaining things we'll discuss in the next class. Thank you.